Bien, bonjour à tous et donc bienvenue à la soutenance de thèse de numérique Go. Donc la soutenance sera en anglais. So I will now switch to English. So my name is Xavier Leroy, professor of software sciences at Collège de France, and I will be chairing this jury. And so we have 3 other jury members who are online. Maybe you can introduce yourself right now.
I'm Derek Dreyer of the Max Planck Institute for Software Systems in Saarbrücken, and happy to be here.
Hello, my name is Bas Pitters. I'm associate professor at Aarhus University in Denmark.
My name is Sarah Lasky, and I'm a professor of law at Northwestern Pritzker School of Law in Chicago.
Okay, thank you.
I'm Evelyne Contegent, senior researcher at the Laboratoire de méthodes formelles, Formal Method Laboratory at Paris-Saclay.
Oh, I'm one of the supervisors, Karthikeyan Bhargavan from Inria Paris.
I'm one of the supervisors. I'm Jonathan Fritzenko from Microsoft Research.
All right. Well, thank you, everyone. So le jury est constitué, as we say. So, Denis, now you have 45 minutes to present your PhD work to us. Thank you.
Hear me? Can all the members of the jury and the audience hear me?
Looks good.
Looks good. So thank you very much to everyone, and especially the jury, for having come to my defense or attending it in video conference as these trying COVID times forced us to do. I'm going to present to you my work today around proof-oriented domain-specific languages for high-assurance software. The layout of this talk is going to be the following. I'm going to introduce the context of my work. Then the main thesis of my work, which will be a vision for using domain-specific languages to improve the applications of formal methods into many sectors of application. Then I'm going to illustrate that vision and that methodology with an example, Catala, a domain-specific language for the law. And finally, I'm going to conclude this talk. So let's start with the introduction, which will set the context of this work and also give way to the main statement there. So my work is all around critical software. Critical software is the kind of software that's deemed too important to fail. And there are some examples of critical software which are quite obvious. You don't want a plane to fail, because if the software of the plane fails and then the plane crashes, a lot of people are dead. However, there are also more subtle critical software examples. One of the specialties of my team, Prosecco, is the cryptographic software. Cryptographic software ciphers and deciphers your communications on the internet, so that when you log it into your bank, the credit card details are not leaked and cannot be seen by the people that are spying on the network. However, there's also a critical software where you don't really see it. And one example that I noticed during my work is the computer program that computes the amount of taxes you owe to the state. And this is a critical software because it has to run every year for all the population. And if there's a bug in it, then it means that people either pay too much or too little tax, which are two different kind of problems, but that can have serious consequences. And we as a field for methods are here because all those critical systems, they have bugs, and they have bugs everywhere. They have been for a long time, and they will continue to do so. And as an example, it is customary that I present to you the example of the Ariane 5 rocket that exploded due to a software error. But I'm going to use another example, which you may have not heard of, which is the Louvois software for the French army that was deployed in the 2010s. And the software is so full of bugs that soldiers had received zero salary for literally months, and their family was like starving and forced to go to food banks because of that. There were like silent demonstrations and hunger strikes, and this lasted like years, and the government was forced to put hundreds of millions of euros just to fix the software, and it's not over yet. So this is some kind of failure of a critical software that we don't want to happen. And our kind of mission as the formal methods people is to raise the level of assurance of those software to eliminate or reduce partially or totally the number of bugs that are inside them. And the question in the field is, can we prove the absence of certain bugs? Because that's what we do in the formal methods people. And the answer is yes. And there are many industrial successes in that area. So I'm going to set a few of them. It's not exhaustive, of course. So you have the Astray static analyzer that was used to prove that the software used in Airbus planes does not crash. So it's useful to know when you're flying the plane. You have the SEL4 microkernel that's been used as a verified foundation for a lot of embedded and low-level software that's been running on critical devices. And of course, you have the Concert compiler that some members of the jury know well here, which is used as the basis for various developments because it ensures semantics preserving compilation from C down to assembly, securing a critical link of the chain of trust. So all of those industrial successes, they are powered by what we call program verification. And the gist of program verification is that you want to prove a property about the program that must hold for all inputs of the program. And this is kind of a theorem. And some of these properties that we might want to prove are the following. We may want to prove that the program does not crash, as did the software, the Astray static analyzer. We may want to prove that memory is accessed correctly, which correlates with the fact that it's not crashing, but there are subtle bugs that come from wrong access of memory. We also may want to check that to prove that secret data cannot leak, which is useful in a security context. And in general, we also might want to prove what we call functional correctness, meaning that the program should behave the way it is supposed to behave. And we specify the way it's supposed to behave in a more high level. So in order to prove all those properties about the programs, I'm going to show you an example of proof architecture that is commonly used. We use it a lot at Prosecco, but it's also used in other works in the literature. So the cornerstone of a program verification endeavor is the high-level specification. So the high-level specification is supposed to tell how your software behaves, but it should be high-level enough so that you can read it and review it and make sure it's correct. And you really have to interpret that this specification is the source of truth for how your software should behave. And then to be really sure that this specification is how you intend your software to behave, you can actually prove some domain-specific self-coherence properties about your high-level specification. So in the case of cryptography, we might write the high-level specification in F***, but we might prove certain properties. If the software is a cryptographic protocol, we might want to check that the protocol possesses the properties of confidentiality, meaning that the messages that are exchanged on the network cannot be read by an external attacker, or authentication, meaning that there cannot be somebody spying on your messages that pretends to be someone else that the one who you want to talk to. And these two blocks are here for really refining and making sure that you really got the intended behavior of the software right. And then you're going to prove that this intended behavior of the software matches or is functionally equivalent to a low-level optimized implementation. Because nowadays, you really want an optimized implementation because you want to go fast when you're subject to performance constraints, because you're running on a server and there's a lot of connections incoming, but you also might want to save energy, right, to reduce the runtime of the software. And in the context of F***, we used to do that with the low star DSL that's within the F* proof assistant. So recently, when I reviewed the literature, I found that there is a common pattern that's used by many program verification developments, which is the kind of integrated approach to program verification. So in this approach, you use the largest proof assistant, usually COC, in order to encode everything that you need to know about both your programs, but also your languages. So you will define all your languages and intermediate languages inside POC, and you will prove some the meta theory of those programs inside POC. Then you will write, implement, and prove some the certified compilation steps between those languages also inside POC. And then the consequence of those steps is that you actually need to write the programs that you want to verify inside POC. So everything is integrated within the same proof assistant, and this has a huge benefit that there are no semantics mismatch, right? Because you can prove everything within the POC assistant, which itself is a foundational approach to proof assistant. So the level of assurance is very high, and it's really the maximum thing that you can have, even though there are some improvements that you can always make on the margin. And this approach is illustrated by the Fiat framework for designing DSLs by the team led by Adam Shipala in MIT. And the end result of that methodology, which produced significant results and is valued in the literature, is that if you have to write the programs that you want to verify in this form. You have to write them as POC definitions inside languages that are a mix of deeply and shallowly embedded, and the syntax is the one of POC. And so my point is that the future that we want for domain experts to be able to review these high-level specifications. Because by forcing people to write everything inside POC, we may get further away from the people that actually need to review and make sure that the basis and the trusted base of our programs are correct. And this observation led me to introduce the main thesis of my work, which I've detailed in my introductory chapter, and which I've dubbed connecting proof programs to proofs with nimble languages. So in this section of the talk, I'm going to explain what this methodology is and how I propose an alternative vision to improve the reach of formal methods into more and more industrial applications. So to begin with this thesis statement, let's start with the chain of trust, because this is really something that you have to control when you're doing a formal verification development. Indeed, the formal verification endeavor is as strong as the weakest link of that chain of trust. So you really have to examine all the links of that chain of trust. So let's start with the executable binary. Usually, if you go one step up, then you have a low-level representation of your program in the compilation platform that you're going to use. It can be C, it can be LLVMIR, and we are lucky enough to have a certified compiler like ComCert that can help us guarantee that the compilation step from the low-level representation to the executable binary is semantics preserving, and then it's bug-proof in a certain way. If we go higher up in the chain of trust, you have to make sure that the semantics encoding of your compilation platform language inside the proof backend, the proof assistant you're doing, is really tight, right? Because as members of the jury may know, the semantics of C, for instance, are really tricky to get right, and there's a lot of corner cases and undefined behavior. So when you embed those semantics inside the proof assistant, you have to make sure that these semantics are correct. And there are a lot of work in the literature that aim to do that. We have the Bedrock framework developed by the Shipala et al. At MIT for assembly, the assembly language. We have the CSys encoding that was used for SEL4. We have, of course, C-Lite that's used by ComCert. So this is all pretty covered in the related work. Then, if we go still up the chain of trust, we have to perform the tricky translation pass from the high-level specification of the program into the low-level optimized implementation that I was talking to you about. And here, you also have a lot of frameworks that exist inside the literature. Like we can cite the IRIS framework developed by a member of the jury to reason about concurrent programs with separation logic. But you also have fully fledged proof assistants like Daphne that help you perform those proofs with respect to a high-level specification. But then the question I ask is, what about the last step of that chain of trust? Who reviews the specification and who makes sure that the specifications are correct? And you might say in the context of cryptography, oh, but if you prove the security properties like authentication and confidentiality in higher level proof assistance, you have some kind of meta-coherence on those specifications. And I say, yes, it works for cryptography, but it might not work for other domains. And law, which is a domain I'm going to introduce to you later in the presentation, you can't really prove the mathematical perfection of the legislation you have to write your software as the law tells you, and the law is a social construct. So you need to get the domain experts to review your specifications. And this is a last step of the chain of truth that I chose to focus on for a large part of my work. And in order to close the gap and to improve the assurance on that link of the chain of trust, I used the approach of using proof-oriented domain-specific languages. So you have general-purpose programming languages, but you might also want to choose to create domain-specific languages in order for the domain experts to have a concise program and a program that they can understand in order for them to be able to review the program. And generally, if you use a domain-specific language, the program is more concise and it uses the correct logical paradigm for you to be able to express those specifications. Of course, domain-specific languages come with a lot of drawback. One of the first drawbacks is that you always have to reinvent the wheel, right? Because all of the domain-specific languages, they usually have functions, so you have to reinvent having function, you have to reinvent having structured data, etc., etc. But also, there is a drawback for domain-specific languages, which is that depending on their implementation, it might be difficult for you to access popular libraries that are used effectively by software engineers or domain experts within their fields. However, to that drawback, I might say that you can choose to offset it by having an embedded implementation within a popular language that lets you access those libraries. But you can also choose to have a completely external implementation that lets you choose your own syntax in order and to expose your own libraries to make sure that what you expose to the user and the domain experts is really what they're used to when reviewing the specifications. Of course, the drawback of that is you need PL expertise in order to craft both the programming language and its implementation. And this is difficult to come by because there aren't a lot of PL experts and their role is usually not very well considered in companies other than the big companies that have like in-house special teams of PL experts. However, there's an advantage to that offsets kind of this need for PL expertise is that nowadays there exists language workbenches that can be leveraged to implement more efficiently and easily your domain-specific languages. We might cite the case of Racket, or we might cite the MPS workbench for commercial solutions. But the biggest of the drawbacks for domain-specific language is the small community of users that the domain-specific language is bound to have. And this is a real problem because having a small user base, meaning that you have less resources to maintain the language, less resources to develop libraries, and overall you have less support for all the goodies that you want to come with a language, right? The development environment, the linters, etc., etc. However, to kind of reflect on that small communities argument, I would cite the PhD dissertation of Theo Zimmerman that says that the largest proof assistant that's used by our formal methods community, Cox, suffers from the same drawbacks as a small domain-specific language would. Theo Zimmerman says that Cox lacks the huge environmental support that designer of a language within a large company can benefit from, and a high level of expertise is needed to contribute. And this is quite okay given the academic original nature of Cox, and that later expanded into more industrial applications. However, given that I don't think that we have enough formal methods people to create a large enough user base to counteract that small communities drawback of domain-specific language, I would suggest that we go all in on the small communities aspects and have like one language maintainer which would be able to kind of maintain the language and provide all the necessary support for language that is needed. But we need a social position for that maintainer of the language. So based on those insights, I will propose a novel methodologies for pushing the verification frontier, which is alternative and complementary to other approaches that exist in the literature as the integrated approach that I cited earlier. So the goal of that methodology is to apply formal method techniques to existing critical code bases to raise their level of assurance, which is a standard goal for program verification. So the first step of this methodology is to carve out the critical subset of the code base, because when you approach in the industry a typical code base, one part of the code base may be dealing with the UI or displaying of the data, and this is not something that we want to verify because it's not really critical software. So the first step is to carve out this critical core and isolate it from the rest of the code base with a cleanly defined API that comes into the formal function. And this is a traditional software engineering thing. It's called separation of concerns, and you might you should apply it everywhere, but this is like the first step of methodology. Then the second step is we go in and bring our PL expertise. We look at the critical core, and we're going to isolate the language that we need in order to express the programs that are in that critical core. And here you might need two languages. You might need one language for the high-level specification, but you also might need another language for the optimized implementations. And those two parts of the critical core, they can live in separate languages. It's fine as long as both are formalized, and it's you as the PL experts to your duty to come and formalize those language subsets. When you have formalized those language subsets, you can write a compilation pass that is going to translate those programs into an embedding, whether it be shallow or deep, inside a proof backend. And this is the step that's really important, because you need to make sure that the semantics of the language that you have created are aligned, so you have to prove them sound, both theoretically but also empirically, because if you're designing an embedded domain-specific language, you need to test that your semantics are actually in line with existing work in the literature, or like the standard test suite of the language, for instance. So the next step is the traditional step of program verification. Once you have your high-level specification, your optimized implementation, both inside the same proof backend, you can actually perform the proofs, whether it be correctness, functional correctness, memory safety, security properties, etc., etc. There's a fifth and optional step, because if you stop at the fourth step, then what you have is you've proven correct a formal model of what your programs are. But you can go a further way, which is you can extract that optimized implementation that you have proven correct into another programming language like C. And if you prove that extraction correct, then you can take that generated code and plug it back with the rest of the original code base in order to kind of close the loop and benefit from this extracted code down directly at the interaction with the rest of your critical code base. So while I've described to you the technical steps that are that constitute my alternative methodology for pushing the verification frontier, there is also a social and organizational aspect that comes into putting up and organizing all that work. Because for doing all the steps of the methodology, you need interaction between the domain experts that are supposed to tell you how the program behaves, the software engineers that maintain the code base in which the program is written, and the proof engineers that are going to do the heavy lifting of proofs to prove that the program is functionally correct, for instance. And in my alternative vision that I propose, the role of the language architect, the PL experts, would be to go and discuss with all three categories of actors involved in the process, and to design interfaces that will allow these people to communicate effectively when for reviewing the code base, for maintaining it, but also for proving proofs on them. And those interfaces, I think, can consist of domain-specific languages, and more specifically, proof-oriented domain-specific languages, because when you design a domain-specific language, you have to keep in mind the fact that later the programs written in them are going to feed proof backends. So it puts hard constraints on the semantics and the way your language is designed. So if the language architect manages to create all those interfaces, then we can have enhanced collaboration with the people and push, hopefully, the verification frontier for this critical code base. So I've presented to you my methodology, which can sound very abstract and very theoretical, but I hope that my work provides a number of examples that can illustrate that methodology in action over several domain-specific languages that I created for two different areas of application of formal methods. The first area is cryptography, and my first contribution presented in my dissertation is lib-signal star, which is joint work with Jonathan Frizenko, but also Benjamin Verdouche and Kartikeyan Bhargavan. And it brings the custom cryptographic protocol, namely Signal, to the web stack, enabling to raise the level of assurance on web applications that were previously using JavaScript, unverified JavaScript programs in order to run the protocol. I also designed the Hackspec language, which makes formal cryptographic specifications more accessible within the Rust programming language that's more and more used by Rust programmers and Rust and cryptographers in order to specify their work. And this is joint work with Kartik again, but also Franciscus Kiefer, which is a cryptographer that loves Rust, which is present in the audience. And finally, in the domain of cryptography, but also going outside cryptography, is Steel, which is a domain-specific language more in the proof backend level that aims to separate the proof obligations that are present for low-level programming by distinguishing the memory safety-related proof obligations from the functional correctness and other proof obligations. And this is joint work with people at Microsoft Research as in CMU, and with Emery Frommertz present in the audience as the lead author. Finally, there's a second area of applications because I took the same techniques that I used in those other contributions, and I tried to apply them to a new domain that has been rarely touched by formal verification people, which is the one of legal expert systems, software that has to follow the law. And the first contribution is that I went to see how the French income tax is computed, and I discovered that this was written in the domain-specific language. So I retro-engineered a compiler and gave a formal semantics to that domain-specific language, therefore improving the level of assurance that's involved in the computation of our taxes. And this work is actually coming into production at the DGFIP as we speak. Finally, the last contribution of my work is Catala, which is kind of an improvement over Mlang and the domain-specific language that the French tax authority has. And this new Catala language enables a formalization of our collaboration with lawyers when producing and maintaining the legal expert systems. And this contribution, that is both my last chronologically in the time of my PhD, but also I deemed the one that's most faithful to the spirit of my methodology, I'm going to dive into it and present to you a little bit more about the technical contents of that work. For the other contributions, I refer you to the dissertation for more details. So let's talk about Catala, the specification language for the law. So since we're dealing with law and algorithms, I'm going to make a series of disclaimers because, and to state the things I will not do inside this work. So I won't try and create robot judges because I won't try and touch to any decisions that involves a judge, right? Because if the law says a judge has to decide, then the judge decides, and we're not going to try and touch that. The second is that the decision procedure that described within the law should have no ambiguity. And this is a hard criteria because, as you will see later, the law has many ambiguities, and this is for a good reason. And finally, the decision procedure should talk about quantitative data and involve tedious computations because we want to automate the procedures that are the most tedious to do in order to create value for the administrations or the organizations that want to automate their processes. The quintessential target for that combines all of these properties is tax law. And I'm going to bring examples from tax law later in the talk, but bear in mind that this domain-specific language could be used for other domains of the law that share these similarities with tax law. So to start and to kind of motivate the need for a domain-specific language for something that from the exterior can be viewed as a very easy operation, right? You just take the tax code and you follow what it says and you just create an algorithm, right? It should be simple. So actually, when I approached this problem at first, I had the same opinion. I thought it was really simple, but the more I looked, the more difficult I found that turning law into code was. And I'm going to share to you an example that comes from the US tax code and more precisely the section 121. So this section 121 is talking about the situation where you bought a house a long time ago, and then you sell it, and then you make a gain, right, from the difference between the price of the sale and the price of the buying. And then this gain can be considered as income, so you should be taxed on it. But there's a provision of the tax law that says, oh, in certain conditions, you can exclude that gain from income, meaning that you're not taxed on it. And this article states the condition for you to be able to do that. So let's read it. Gross income shall not include gain from the sale or exchange of property if So it sums up what I was telling to you earlier. We're defining the income exclusion quantity, how much you can exclude from income. So if the condition is met, then you can exclude the gain from the sale or exchange, or else you can exclude $0. Let's continue to read the law. During the 5-year period ending on the date of the sale of exchange, such property has been owned and used by the taxpayers and the taxpayer's principal residence. So here, the law wants to prevent situations where you buy 10 houses and then you make a surplus and then you sell every one of them and then you get tax-free on all those selling rates. You can only use that if it's your principal residence. It's to limit the kind of opportunities that this mechanism introduces. So here we have to know what were the periods in which the taxpayer owned the house and in which periods it's used it. And then we have to truncate those periods within the last 5 years. And here you can see there's an ambiguity, right? Because the question is, do you have to own and use the house at the same time? Or can you like own the house and use it at different times? And this is tricky, right? Because you can like rent a house, then during a certain period of time, then you can buy it and then later sell it. So how do you compute those things? And actually there's an interpretation of the law that's been stated in regulation, which is the official interpretation by the IRS authority, the American tax authority, that says that no, you have to compute those periods distinctly from each other. So here you can see that there was an ambiguity and we had to resort to legislative interpretation in order to code it in the right way. Then if we go later into the law, you can see that you have to aggregate those periods and compare them to a 2-year threshold. But here again, there's an ambiguity because what is a year? Is it 365 days or is it 366? And this is a valid question, right? Because depending on the year, so there's a problem. And then again, the law tells us that here in that specific circumstance, you have to interpret 1 year as being 365 days, even though it may land on a bissextile year. So all of these are like actual questions that you need to ask yourself when you're coding up the law, because it can mean a big difference between the people that can deduct the gain from the sale of their house from their income or not. And then there's another provision that caps the gain, so it adds another round of complexity, but I'm not going to code up to you because you've understood the gist of the example. So because this is a hard problem, I say, okay, we might be hitting some kind of a hidden critical software problem here. And I investigated what are the different legal expert systems in productions in France inside the administration. The good thing is that the administration is obligated to publish them because there's a law about that. So I could like investigate and see what were in which languages they were implemented and what was the size of the code. And you can see that the size of the code is quite big. We're talking about tens of thousands or hundreds of thousands or even millions of lines of code. And they're coded up in languages that are very diverse and sometimes a little weird, right? For instance, you have that SQL implementation of payroll taxes that's 20,000 lines of code. Good luck for debugging that, even though I'm sure the people doing that have high expertise and they know what they're doing, but this might not be a conventional choice, right? And moreover, some of that code is still closed, right? Even though there's a law that says that they have to publish it. So you might say, okay, maybe France is a very bad country, and in other countries it's better than that. Actually, it depends. For instance, in the US, which some of you might view as like the leading example in the world, right? The income tax is still implemented in the assembler of a computer that had been created when Kennedy was still president. And this is a huge problem, and there are news articles talking about that, and that the IRS doesn't know how to modernize their tax system. But you can see that there's a similar pattern of critical code that's running inside basically all developed countries. It's huge chunks of code that they govern huge aspects of people's lives, whether it be tax law or social benefits, and nobody has. I mean, the interest that those systems attracted is very low in the research community. So this motivated me to look more into the problem. And this is where I discovered the amazing works of Sarah Losky, who is also in the jury, and that really laid out the non-monotonic legal reasoning structure for tax law. She based her works on insights around more general legal reasoning made by the logic programming community in the 80s and 90s. And Sarah-Lowski really puts out that when you read the statutes, there's a similar structure, and you don't have to read that blob of text. It's too big and big to put colors, so don't worry. So if you kind of parse that paragraph, you can see that there's a base case here for computing that the consequence something is substituted by another thing. But then the paragraph B introduces an exception to that base case, and the exception has a different consequence. And when you want to translate that into code and to run the code, you first have to see whether the exception matches, and then if it doesn't match, you go to the base case. And this is completely backwards with respect to the way that programmers usually think, where they first match the base case, and then else, if there is an exception, they will introduce that if then else triad, right? And this is a big pain point for people that translate law into code, because they have to use conditionals to translate that non-monotonic legal reasoning. And this makes for word encodings and difficult translations that make the code harder to read and harder to review correct. Moreover, I continued my investigation, and I tried to see how this code was validated right in production. And what they do is that they use test cases, which is completely okay. A lot of people use test cases, and you should write test cases if you want to be a good software engineer. The problem is that there's a common pattern of under-testing in those software. And this under-testing doesn't come just from like the traditional incompetence or like a lack of funding that the agencies have. It has more to do with the structural, even though they lack funding and they should get more funding. But there's a structural problem that comes from the fact that the behavior of the program has to be specified by lawyers. So first, if you consider the combinatorials of the input space for the systems, usually you need thousands or dozens of thousands of test cases, because, for instance, in the US income, in the French income tax, there's 1,500 input variables for you to fill your income tax. So you need not only 1,500 tests, but like the combination. So it's square roots. It's the square of this number, right? If you want to test the bilateral interactions between those input variables. So you can see that if you really wanted to cover all situations, you end up with a number of tests that's completely astronomical. Moreover, these tests, they have to be reviewed and updated each year after each legislative change, right? Because apart from the case where you have a fancy system to map the test to the code that it actually tests, you don't know whether a test is effective by a change or in the code or not. So lawyers have to review all the test cases, and lawyers are costly, more costly than programmers. So this poses a problem because of the structural problems. There are a few test cases. These test cases are not validated as thoroughly as they should be, and this led me to think that we need a complementary and an alternative method to raise the level of assurance on the code, and we need a better communication medium between lawyers and programmers than test cases to efficiently have that review of the code. And this is where Catala enters the stage. So Catala is a language that's made to be able to mix code and law in a single document and make it easy for lawyers and programmers to work on it in a pair programming fashion. So in this work, there are three major contributions that also were published in the ICFP article last year. The first is that we create this domain-specific language that's usable and reviewable by lawyers, and we made early user studies for that language. We formalize the semantics for the legal reasoning that's used by Catala based on the insights of Sarah-Lowski and prior work. And we implemented a compiler that we partially certified with respect to the key computation step. So without further ado, let me present to you Catala, this language that's supposed to be reviewable by lawyers. So here you can see there's an excerpt of the US tax code, another one. So here, what it says is that if you work for a company and that the company gives you something that it produces, like let's say the company produces cars, and the company may give you a car at a really lower price than what the customer price is. Then the tax code says, oh no, you can't do that. You can't like sell a really lower price. There's a limit on how much the gift you can do to your employees. And this gift, for instance, in the case of property, it's the gross profit percentage, meaning that you can't sell at loss to your employees. And this is how it's defined in Catala. So you can see that we define the variable qualified employee discount with a condition if the property, so if the thing that's gifted is a property, then you have this complicated formula to compute with respect to the gross profit percentage. And you can see first the syntax is verbose. It has English keywords, and this is on purpose. It's made for lawyers to be able to review it, and we've tested that empirically. But there's a semantics and an unusual twist, because if you go further in the law to paragraph B, we're defining again the same variable qualified employee discount, but in the case of services. And here, because in the services we don't know the gross profit percentage because it's difficult to measure, the law says it's 20%. And here you can redefine that variable qualified employee discount, but with a different condition. And you can see that in Catala you can specify the definition of a variable with little piecewise definitions that will later be glued together in order to make the definition for the whole variables. And then you have a mechanism to declare exceptions to let you encode that non-monotonic reasoning. And everything is accounted for in those little piecewise definitions. So underneath the surface syntax, there's a formalized core, which is based on lambda calculus, because lambda calculus is simple and we like it. So here's the syntax of lambda calculus, and the only addition we're going to make that's sufficient to model Catala programs is a default term. And the syntax of the default term is the following. So on the left of the middle bracket, the vertical brackets, you have a list of exceptions. So basically, when you're going to evaluate that term, you're going to look whether the exceptions are satisfied or not. And if they're satisfied, then you take the exceptions. Or if they're not, you're going to go to the base case. And the base case is on the right of that vertical bar. So you have a condition for the base case, which is on the left of that turnstile sign, and a consequence on the right, and both are expressions. And of course, there can be difficulties with evaluating that term. For instance, consider the case where two exceptions happen at the same moment. Then the law might not have foreseen that two exceptions can happen at the same time, and you don't know which one to apply. Is it this one or is it this one? Because the two leads to different values. Here, we've discussed it heavily with the lawyers in the team for Catala, meaning Lian, Hutner, and Saralowski. And we deemed that this was kind of a design failure in the law, because the law ought to specify the hierarchy between exceptions to know if both are valid at the same time, which of the two you have to execute. But there's also the case where no definition applies, but you have to compute a value for the variable. So instead of dragging this undefined value, which we don't want because it's a $1 billion mistake, it raises an empty error that has a semantic of an error, and that's is brought to the new program. So this semantics can be formalized. So you can see that here, when we have no exceptions that are evaluated, and the condition for the base case is false, then we'll return the empty error, right? Nothing applies. If the condition for the base case is true, then we'll return the consequence of the base case. If there's one and only exceptions that trigger, then we return it. And if there are multiple exceptions that trigger, then we return the conflict error. And this is the semantics that we need. This is it's quite a simple semantics that it fits on one slide and it's presented in an article. And there's a lot of work that had been going on in that formalization work, so that it's really simple to present. So then, if we want to deploy Catala programs into production, we went for a compilation approach, where we compile the programs from lambda calculus into the programming language that you need, because lambda calculus is versatile. You can translate it to basically whatever you need, because you just have lambda calculus and arrays and computations on dates. And this you can have is in many languages. So you can translate to C for batch computations, you can translate to JS for online simulators, you could translate to R for economic models. And this is all implemented backends or future work that we aim to give at the Catala compiler in order to provide the source code Catala program as a library, as a code source library in the programming language that you need. If we want to, so of course there's a compilation step involved here, and the compilation of this default term involves some kind of an accumulator that's going to process all the exceptions, count them with an option type, and if The option time is on some case, then an exception as triggers, and you count it. And if none, then you just evaluate the base case. And this process exception helper is just a fold left with some kind of counting logic that lets you do the counting as was present in the schematic. So this compilation step has been formalized and has been also implemented in the Catala compiler, which features an architecture with multiple passes and multiple intermediate languages inspired from the best architected compilers out there. It has 13,000 lines of YAML. It's looking for contributors, and if you're savvy for that. And it's of course open source on GitHub, published under the Apache 2 license. Of course, because that compilation set that I showed you is kind of tricky, I want to ensure that I didn't do any mistakes in the compilation, so I went to prove a simulation theorem for this compilation step to prove that it's semantics preserving. And here's the simulation theorem that I ended up proving. So you can see if you start with your ED term that evaluates that steps to ED prime, then the translation E lambda of ED and the translation E lambda prime of ED prime, they both step with an arbitrary number of steps. This E targets the same, the common E targets value. And this is quite a little bit twisted because normally you would have like a square for the simulation theorem, but here the order of evaluation might change. So here we have that common target, but since the language is pure, it doesn't matter because there are no side effects. We have proven this theorem in the F-star proof assistant for a proof that's about 3,500 lines. So for future work, and just before the conclusion of this talk, I'm going to present to you some kind of ongoing thoughts that we have about turning Catala into a proof platform. So, of course, if we have formalized programs that are supposed to follow the law, we're going to prove properties on them, right? Because we're formal method people. And the property we might want to prove about the programs, they fall into two categories. So inside the framework of the Catala semantics, we want to prove that the execution is well behaved, meaning that there are no empty errors or conflict errors that are raised. And this is important because it signals that the law is well drafted, right? There's a rule that applies in every situation and no two rules overlap with each other. But we also want to prove high-level functional properties about the programs, like is the marginal tax rate too high or not? This is a question that has been asked by the Constitutional Council in France. And in order to tackle the complexity of those proofs and really to make it possible for us to do it with off-the-shelf tools, we want to use the proof by refinement strategy, where we start with a P0 program, and we are going to apply syntax-directed program transformations in order to transform it into P1, etc., into Pn, and with the hope that Pn is simple enough to be able to perform high-level functional correctness proofs on it. And we might also generate, during those simplification transformations, a verification condition which we can discharge to a verification condition purpose. Of course, this is a future work, so it's not yet fully sketched out, but I invite you to come to the Prolala workshop at Purple to know more. As a conclusion of this talk, and I'm already a few minutes late, the conclusion has come. Okay, so the conclusion will appear in a slightly offset format. So I will kind of conclude the talk by a hot take, which may or may not be justified by the work I have presented in this dissertation, which you may or may not agree with. I'm open to discussion, which is that the applied formal methods as a field has focused maybe a little too much on technical issues in niches of application like cryptography or kernel verification, etc. And those niches, they have diminishing returns in terms of the proof, the proof engineering that you have to put inside them to get better results as it goes by. And the complexity of frameworks that are crafted by people inside the field, but also perhaps members of the jury, is quite astonishing. And I would say I admire their work, and I think it really goes forward as a field. But maybe there are simpler areas where we can apply more simple techniques of PL and get expand the reach of PL forwards without spending years and years crafting those beautiful and elegant proof frameworks that are very complex. On that note, if we look at the Pliers paper by Pavlet and al. That's recently been out, when they try to take a very user-centric method to designing this kind of domain-specific languages, they found that the designing and running of user studies to assess whether a feature of the language was useful or not for the user took them more time than to implement the feature. And I think this is a sign for us to kind of look more towards the user and maybe select features that are less complex technically, but that may bring better value for them, as we feel. But these are very perspective thoughts, and of course, I hope that my work reflects them, and I hope to that my future work will be guided by this principle in the future. I want to thank you very much for having attended this talk, and it's time for the questions from the esteemed jury.
All right. Well, thank you, Denis. Now you can catch your breath. Okay, so we move to the questions from the jury. And traditionally, we start with two reviewers and in decreasing order of distance. So I guess it means that Bas should start. Bas, are you ready?
Yes, I can start.
Okay, go ahead, please.
So, Denis, thank you for the very nice presentation, and it's impressive. I mean, how so you created a synthesized research program, and you looked at what people had been doing for a long time, and then said, well, actually, that this should be done differently. And as Derek wrote in his review, I'm guilty as charged, and this certainly also holds for me. So I've been building monolithic systems. But recently we've actually been working with the tools you've made, the Hacspec language. So I want to explain a little bit how we've been using it, and then you can tell me whether we've been doing it right or wrong. So the thing we've been doing is trying to make a high assurance implementation of the BLS curve. It's an elliptic curve implementation. What we did was to implement it in your Hacspec language, and we're now interacting with the IETF, the Internet Engineering Task Force, on actually getting it used as a reference implementation, and they seem excited. So congratulations for this. This seems like your thesis actually works quite well. What we've done is you provide both an EasyCrypt and an F-star implementation. Of course, the first thing I wanted to do was go back to my favorite monolithic system, COC, and we connected it up with the Fiat and Bedrock system that you mentioned before. And from this, we made a high assurance implementation. The first question is, does that actually fit your thesis? Is that the right way of doing it, or should it be done differently?
First, thank you very much for that account of what you have done. I think it's really impressive, and well, thank you for using my system. I don't think I'm the one that has to police whether people are using my system right or wrong, right? I'm glad that people are using it, but yes, it seems completely in line with the spirit of what I was trying to do. So I'm really grateful for you to having experimented with that, and I hope it continues to be useful to you in the future.
So it's certainly very useful. I think that there are a lot of uses for this in the future. What we can hope to do is to have many of the internet standards just come with a reference implementation in Hacspec. So I see a lot of possibilities there.
So if I may, that was also the goal of the original Hacspec that was done by Kartik, Franciscus, and others, but written in Python at first. And it seems to me that the choice of Rust is bringing more attention and more hype to the language as a standard than the Python was. So maybe it's a good thing that we switch to Rust.
I have the same impression, but of course that's something that we need to find out. The other one I want to now turn to the your work on verifying low-level code using Lodestar. Could you compare the code? So again, my apologies for coming back to the work we've been doing ourselves, but it's the easiest way for me to relate to the work you've been doing. So what we've been doing is connecting up Hacspec and Fiat with Rust, and in this way you could, of course could also generate WebAssembly. So could you compare and contrast with what guarantees you get from generating WebAssembly in that way with generating WebAssembly in the way you're doing it?
So thanks for bringing to my attention the fact that Fiat and Bagrod now generates WebAssembly. I think that's
they generate Rust, and then from there, of course, you need to trust.
Oh, okay. I see. Okay. Well, of course, Fiat has a more foundational approach than the one we had in FStar. So I guess that you have more guarantees on the certified method compilation from the high-level code down to the generated Rust. So that guarantees you get better from Fiat. The question is, in my understanding, Fiat, you had to really tune your compilation algorithms to the specific kind of algorithm that you were implementing. For instance, I know that they have curve implementations, which you specify just the modulo of the prime field, and then it just extracts all the code. But all that code to generate that curve implementation is done by hand. So I don't know, maybe it's a little bit more difficult for you to set up that infrastructure for the kind of primitive that you're encoding, but compared to Lowstar, but also Lowstar, you have to write more code manually, and the more code that you write manually that's not backed by your functional correctness proofs, the more chances of bugs you have. I would say that's a comment.
That sounds like a fair comparison. Looking at the same work, you connect up FStar with ProVerif, and of course that is something that's a very interesting question. How do we connect up the computational and the symbolic model in cryptography? Could you say a bit more about what kind of guarantees you get in that in the work you've done?
Yes, in the work I do, there are no formal guarantees because there is no automatic translations. Of course, we review that the ProVerif model is accurate with respect to the FStar specifications, which empirically is fine to do because ProVerif uses some kind of a syntax that's close to the lambda calculus, so the ML family of languages that's used in FStar. In the future, the Prosecco team is aiming to connect cryptographic to FStar, and Benjamin Lip, a student, is working on that currently. But so far, we don't have like top-notch guarantees for that link between the computational model and the high-level specification.
Thank you. I have two more questions, two short ones. I hope that I still have time. You want to verify, so you generate WebAssembly code. Now, of course, what you would like is to have a verified compiler, and one of the obstacles to this is you don't have an operational semantics of WebAssembly in FStar, if I'm not mistaken. Yes. So yes. The nice thing is that, of course, by using Hacspec, you have 3 different backends, but in the end, if you want to make a verified compiler, you seem to need to go back to your monolithic system again. Could you reflect on that? Yes,
I think as I said during my presentation, the monolithic system has a huge advantage, which is that formalizing a language inside a system takes a lot of work, and we may want to reuse that formalization, not to have to duplicate the work. And I think we will need monolithic system in the future, right? Especially if you want to have very high assurance foundational approaches where every step is proven sound and every compiler is verified and certified. And yes, there is a formalization of WebAssembly inside Coq. So if you want the verified compiler, then I think, yes, that you will need to go through Coq, right? Or else you need to reinvent a formalization of WebAssembly, which you can do because there's a formal specification, but it takes a lot of work.
Yeah, that would take a bit of work again to redo that. Of course, it has been done in Isabelle before, and that has been ported to Coq, and then you could port it to the other systems again. But yes. So it would be nice if we could avoid that duplication of work. Yeah. Last question, and maybe more of a reflective question. So what you've been doing is formalizing the law and formalizing contracts in a way. Of course, there's also the smart contracts that have been becoming more and more popular, and there what one can see on the blockchains is that more and more regulation is coming. Could you imagine using your language also for smart contracts, for actual contracts, or would one define a new domain-specific language?
So this is a good question that has been asked to me like a number of times, and the answer I usually give is that it depends in what form the governance of your blockchain is written. If it's written in the form of lateral language statutes that's drafted with a base case and exception, then yes, you might use Catala to encode the governance rules that are written within that statute, well, let's say, and then translate them to smart contract code. There's actually a PR opened by a contributor on the Catala compiler that aims to provide a Solidity backend to Catala. However, it's missing some technical works that we've been working on, so it's not yet merged. But yes, it has been considered in the past.
Thank you. Those were the questions I had.
All right. Thank you very much, Bas. Denis, can I suggest you move your camera in front of you? Or you in front of your camera, but I think it's better to move the camera.
I just turned mine on, actually.
Okay. Well, never mind. It all works. Yeah, here we'll have a nice view of the back of your head. Yes. Well, never mind. Okay, so it's time for reviewer number 2 to ask questions, and that is Derek. Derek, are you ready?
Yeah, can you hear me?
Yes.
Great. So yeah, thanks, Denis, for a very nice talk and a very nice thesis. I really enjoyed reading it. It covers lots of different ground, so it's one of the most varied theses I've read. Let me start with a sort of higher level question. So I mean, I very much enjoyed the first chapter of your thesis, especially as a sort of a kind of polemic against doing everything in one system, and I liked it. I agree with a lot of what you have to say, but I want to push back on one thing and get your opinion on it. So, you have this quote from Theo Zimmerman, I think it was, about how easy it is for people to pick up some to get users for something like for something that's developed in Coq, for example. And I would say my experience has been the opposite. That at least for Iris, which is the biggest Coq framework I've been involved with, the reason we were able to get lots of people involved from around the world and developing it was precisely that it was done in, well, there's two things. One, that it was done in Coq, which is something that a lot of people come in knowing something about. And the other was that it was machine checked. And so we were able to get, we were much more confident about receiving contributions from people other than the original developers, because we didn't have to trust them. So I'm curious what you have to say about that in the context of the tools that you have been developing. How much would you trust contributions to, well, any of these tools, but, say the legal tools, for example, if they're implemented in some standalone tool, how much trust is involved there?
Well, thank you very much for your question, and thanks for the comments on the introductory chapter. I'm really glad that you liked it. Concerning your experience with Iris, first, it's very positive for the whole Coq community that we're able to attract that many contributors. And I've seen the workshops that are performed now at every major PL conferences that attract more and more people, and this is really encouraging because I think Iris is one of the ways to go forward to improve the memory safety problems across, and other problems, of course. But you said something. You said that we accept contributions because they're machine checked, so we don't have to trust people. And I would reply to you, yes, you don't have to trust people in memory safety, but memory safety is not the only property, like it's not the only intended behavior of a program. And when your program is supposed to follow the law, whether it be memory safety or not, doesn't teach you a lot to you about how it follows the law.
And for that, we have to rely on the way that the domain experts have to sort it out between themselves, who is doing the thing right. And so we have to rely on that external source of truth and trust. And for instance, in the legal system, the legal expert system problem, the administration is supposed to act legally. And if the administration doesn't act legally, then you can go to court and sue them. So actually, it's the task of the lawyers of the administration to ensure that the code is faithful to the law. And there's a mechanism, namely that you can go to court and sue them, because if it's not, that ensures that the code will actually eventually be faithful to the law. And I see the Catala as just like a tool to translate that dialogue on the correctness from the paper and the situation to the code and the abstract behavior in itself.
Okay. Let me move to some more technical questions. So actually, I mostly want to ask questions about the legal part of the thesis, because that's the one that I know the least about, and I'm found the most interesting. Personally, it's the farthest outside my expertise, but very intriguing. So can you clarify what is the relationship between Mlang or an M++ and Catala?
Yes.
Or is the former encodable or somehow can it be formalized within the latter, or are they totally separate things?
So right now they're totally separate things. However, Catala has been thought of as like a better designed version of Mlang. And if the DGFIP were to use Catala to rewrite their systems in the future, what I would do in that case is that I would translate Catala to an intermediate representation of the Mlang M++ compiler in order to have safe interoperation between the two. But this is not done yet, and we don't know whether the French tax authority is going to accept it or not.
I see. Okay. Is the idea then that Catala will be a kind of universal language for some subset of law? I sort of was trying to understand what exactly is the scope. You mentioned something about the scope in your talk, but I'm still not completely clear what is the envisioned scope of Catala, and how would I know if I have some law whether that can be formalized in Catala?
This is a hard question, because I don't think that Catala is going to be like some kind of universal or monolithic language, because the semantic base that you need to encode law is quite diverse depending on the domain of law that you consider. For instance, there's a paper by James Grimmelman and Shrutarshi Basu and Nate Foster that was published at Splash in 2019 that laid out a semantics base for the property conveyances law, meaning who can inherit which property depending on who person dying and what are the family links between all the persons. And the semantics for that was along the lines of a CTL, LTL kind of thing, which we don't have in Catala yet. So I would say that depending on the domain of the law that you want to formalize, either you just need a lambda calculus and arithmetic, in which case you can use Catala, I guess. But in some other domains of the law, you would need like fancier logics in order to express the objects that the law is talking about.
Yeah, I guess what I'm angling towards is like, can you imagine that? So I guess is the first step to just try to formalize is the first step to try to formalize some further laws in languages like Catala to see what you need in the specification language, and then eventually maybe develop a more universal language in which you can encode. Like, I mean, I'm again related, as Baz related to his work, I'll relate to Iris, right? So I mean, Iris came out of a long line of work on separation logic, where after 1 million separation logics were developed, we could say, oh, here are some key components of these logics, which if we put them together can sort of span the space and allow us to derive many different logics in one framework. So I mean, this is early days yet, obviously, but I'm just sort of wondering, do you imagine that eventually there could be some more universal framework in which you can, for deriving domain-specific law logics?
So this has been a question that's been hotly debated in logic programming circles as in the 80s and 90s. And it turns out that if you really want to capture legal reasoning in all of its diversity, you need some kind of deontic logic, you need some kind of process calculus, you need some default calculus, And you need like very wild and diverse forms of logic to actually combine and talk together. And honestly, so there's a project in Singapore where they are trying to combine all those logics together, but I really don't know how they're going to do, because it seems very complicated to me to create a framework. I mean, there's a team in Paris-Saclay with the deductive framework, right, where they're trying to combine all sorts of logics. And I would say that you should look into that direction if you really want to express all the diversity that can come into play. But it's going to be very complicated, I think.
Okay. Okay, and one last question that's kind of more technical, I guess, is so is it true? So in Catala, is the law deterministic, or are you restricted to deterministic law?
Yes, yes, I am. Catala is not Turing complete.
All the exceptions.
It's deterministic and non-Turing complete. But
okay,
this is hard coded into the language, and for the tax law example, we might want that the tax are computed deterministically. It may not be in all the areas of law, but even if there's a source of non-determinism, we can leave it as an input of the program, and usually that's a decision by a human. You leave a decision to the human, then you leave it as input of the program, and the human can like act as a source of non-determinism.
Right. Yes. So okay. So I guess okay. So then I have two follow-up questions to that. So one is how hard is that baked in? I'm like I could just imagine many laws are non-deterministic, or at least have multiple possible interpretations. Maybe are you imagining that? I mean, I assume that you did this for simplicity, or to simplify the semantics.
Yes.
But is it the case that all the non-determinism that you can imagine in a wider variety of law is actually encodable through just taking an oracle from the user?
So empirically, I can't answer this question because I haven't formalized everything.
Yeah.
You'd have to talk with Sarah Losky. I think she would know better about that, because I haven't asked her the question precisely as you. However, leaving to the user the role of the user to be an oracle as to the interpretation of a law is actually what the legal system does. Because if you go in court, you can choose what you want your interpretation of the law to be, and then there can be an opponent that chooses a different interpretation. And if there's a conflict, then the judge has to settle. So you can see that there's a very complex system of opposing oracles that has been set up by the legal system over the centuries. And I think they've been doing things pretty fine, right? I mean, we should stick to what they decided for that organization, I think.
Okay. Okay. Actually, I think that's my last question. So thank you very much.
Thank you very much.
Okay. Thank you.
No.
Okay. Good. All right, so let's move to the next jury member. Well, Sarah Losky was just mentioned. So Sarah, if you're ready, we'd like to go next.
Yes, thank you. So wonderful project and wonderful presentation. Thank you. I wanted to start with a sort of narrow question that I was just hoping you could expand on. And you say that this is from the paper, we initially envisioned a general override mechanism that would allow a parent scope to override a subscope definition at any depth, but you said we're not going to do this because we can't find a single example of statutory law that needs this feature. Could you, I'm not obviously a computer, could you elaborate on that a little bit and sort of, I'm trying to just get an understanding of what that comment means.
Okay, so it's going to get a little bit technical, but I'm going to try and explain. In Catala, we have this scope abstraction mechanism. And the way it works is that it's basically a function, but it's a function, and you can modify any local variable of the function when you call it, by redefining it, basically. And what this comment says is that, imagine you have scope A that calls scope B that calls scope C. And imagine you as scope A, you want to modify a variable of scope C. And what I said is that you can't in Catala natively you can't modify a variable of scope C if it goes through any direction, because that would be too complicated for the semantics, right? Because and what you need to do if you want to do that is you need to, for scope B, to expose a scope C's variable as a variable of scope B, and then you can modify scope B. And so actually there's a way to encode that modification deep down in the call stack, but you need to provide some extra steps for the system to work. And that simplifies the semantics a lot. I hope it clarifies what that comment.
Yeah, that's very helpful. Thank you. I was wondering, this might be more of an extension of the paper, but I was wondering whether you're developing a theorem prover for this, and if you what benefits, if you are, what benefits or risks you see of something like that?
My plan is not to develop a theorem prover. It's beyond my expertise, and I think I would need to spend a lot of years if I were to try and do that. I would rather connect Catala to existing theorem provers or static analyzers or automatic theorem provers. And of course, each of them have their own weaknesses and strengths. So we'll have to, I guess, empirically test them to see what's the best suited to verify Catala programs, I would say. So empirically, but also guided by the way the semantics of the program and the literature work of encoding different languages in different theorem provers.
And what would making that connection, what would that allow? I mean, so right now you describe a fairly, not straightforward, but you describe a fairly clear implementation, right? So something like somebody gives the information, they calculate tax. That's pretty straightforward. If you were able to connect this to a program like you're describing, what's the potential there or risk?
So this was on my slide where I presented the kind of properties that we want to prove. We may want to prove that the law is well behaved, executes in a well behaved way, meaning that in any situation there's at least one rule that applies, and that in any situations there are no two rules that are exceptions but not prioritized that applies at the same time. But you may also want to prove like high level properties, like the marginal tax rate is never too high, or there is a tax loophole, or there are no tax loopholes, or this kind of properties. And I haven't investigated really what kind of properties we may actually prove, because it depends a lot on the performance of the provers and actually the strategy that we use to prove them. But I think the door is open to applying formal methods to all sorts of questions that lawyers have about the law, and they can't prove because they would have to do it in a manual way, which is too tedious or too complicated to do.
You make a comment at the end about, and you made this comment during your talk as well, about court cases that could arise from this, which suggests that the code itself would have the force of law, essentially. So I want to divide here the idea, for one thing, that you would have implementation of the law. We have lots of implementations of the law that don't themselves have the force of law. If you could challenge the code itself in a court case, that suggests to me that the code would have the force of law. Is that what you're envisioning? Or are you envisioning a situation that seems difficult to manage? Are you envisioning a situation where someone says, oh, the implementation is wrong because it doesn't match the law? I guess I'm struggling with the connection between the code and the law. When does it have the force of the law?
So this is a question about the legal framework of if an administration were to use Catala as its executable program. And this is a question that's not yet settled, and I think Eliane is planning to work on that later in the future. But my interpretation, as far as I'm concerned, is that in a court case, the plaintiff could use the trace of the program to justify the decision that has been taken by the administration, and then it would use the program as just a way to show what steps of the law has been applied. So we're not talking about the program here; we're talking really about the law, and then the program is just here as some way that records the interpretations of the law by the administrations and records the individual justification of the decision taken by the administration. But I guess in the future, yes, if we if there are court cases that center about, oh, but the administration has implemented the law that way, and I would argue it's implemented this way, then we'll need to define some kind of legal status for the code. What is it? Is it an interpretation? Is it some kind of vehicle of enforcement? That I don't know. It's more of a legal problem.
So you see this as more on the interpretation side. Would you imagine the program being used on the drafting side as well? That might be a way to combine, or maybe to not fully alleviate, but partially alleviate some of that. So if it's actually involved in the earlier in the process.
So what you mentioned is what is called rules as code, and it's been the subject of an OECD report a few years back. And it's this vision where you can have co-design both the code and the law together, because when the law is talking about code, might as well like design the code at the same time. And I think I don't subscribe fully to that vision, because I think that the law, because the code only tells you how to compute a thing, but the law is much richer, right? Because it encodes a way to interpret all variety of contexts and apply it to a situation. And I don't think this is something that the code can do. I think that we can co-design code and law together, because if you want to assess the impact of what the legislation reform would be, then you need the code, because you need to run economical simulations, right? So this would be useful when you're co-designing the law. If you have the code that's in sync with the law, you can test the impact of your fiscal reforms as you're designing them. But as a more philosophical thing around designing the code and the law, I'm not really sure what's the added benefit.
So you're sort of imagining something that's almost, I mean, is this accurate? So you're sort of saying the law is much more than just the part that we can put into computation. So you could imagine a situation where portions of the law were coded at the time that it was drafted. So this is like this, in the early 90s, there was a movement within the Commonwealth nations to rewrite tax law. And one of the things they did is that they added some formulas and flowcharts to the law itself.
Yes.
And it did not replace the law, but there were portions of it. So maybe something like that, where instead of adding like a formula or a flowchart, you might add for just the portions of it. Would that be consistent with what you're saying?
I mean, yes. I mean, you could replace the flowchart by a little algorithm in pseudocode if it helps the reader understand what the law means. But I think it's just the primary use is a pedagogical tool, right? It's if it can simplify what the law is intending to say without compromising on the signification and the richness of interpretation, then I think it's fine. But I think you have to be careful when you're doing that.
And so this leads to my final question, which is a broad question, which is, what do you think is the greatest risk of what you're describing? So you've described some various potential problems that could arise. You allude to this at the end with the court cases. But let's say that this proceeds, and it seems very promising. But what do you think is the greatest risk, or the one or two greatest risks that could come from this? The perhaps unanticipated results that might be problematic.
For me, the greatest risk is that if a private group would be to constitute a monopoly on the formal encoding and interpretation of the law, as it is somewhat the case in the US with the commercial tax software. This would be a huge risk in terms of transparency for the users, but also some kind of profit-seeking companies that would just impose an additional tax on the user in order to access the law. And of course, they would use it in order to optimize their taxes and stuff. But I mean, this is fine. You should optimize your taxes if it's legal, right? It's up to Congress to actually fix the loopholes when they have the time. And if they don't, sometimes it's because of parliamentary delays and stuff, but sometimes also there's a political will not to fix the taxes, but then it becomes a political problem, right? So it's also why I put Catala as an open source program, and that I intend to apply it to the public sector first, because I do believe that we need to have this as a digital common, right? This is something that's been alluded to by people at the Direction du Numérique. They're all about trying to build some kind of digital common for encoding law into code, so that everybody can benefit from it and everybody can access it.
Great. Thank you very much.
Okay, well, thank you very much, Sarah. Let's move on to the next jury member. Evelyn, are you ready to go
Yes.
next?
Thank you. So, Denis, I think I have two main questions. The first one is, I understand that you have a unified theoretical approach for performing proofs on domain-specific languages, but during your thesis, you have developed several DSL. Isn't there a danger about having so many domain-specific languages? You talk about Louvois, and then I ask myself, at the limit could be that one piece of critical code could lead to just one DSL. So, and then later you you have this you present this architecture with just one main maintainer for one DSL. So if there is this person is leaving, so
Yes, I know.
it could be very, very damageable.
Thanks for your question. I agree with you. I agree that there's a risk for multiplying the DSLs, and I think it's a tension, right? We don't want everything to be coding in the same language, all the programs in the world in the same language, but we don't want each program to have its own language. So there's a tension, and I think for me, you need to choose the right balance, and you need to assess the risk of having one maintainer. If your software is ready to critical, you can choose to encode it in the mainstream language because you have a lot of maintainers. You can have a lot of incoming developers that come, or you can choose to do it in a DSL, or you can have one expert, but then you need to have some redundancy, right? But it might cost more, right? And I think that's a choice that has to be guided by the specifics of your thing. For instance, in the law, if you were to try to encode the law in a mainstream programming language, you would hit the problems of encoding the non-monotonic reasoning into this mainstream programming language, and it would lead to messy code or code that has this spaghetti form, and that's really difficult to maintain after a long period of time. So I would say that unfortunately, I don't have a silver bullet solution to decide whether you have to do the one or the other. Of course, you need to ask yourself the question, and you need to ask yourself, you really need to consider both options before choosing, because otherwise you're applying like one methodology to everything, and it doesn't apply to everything. That's kind of my view on it. I don't know if it answers your question.
Actually, I wonder whether it's possible to not completely white or completely black, but to have something in between, like a family of DSL for laws, for instance,
yes,
which can share some common part and have different things. For instance, for temporal logic, or to have. Do you think it would be feasible?
I think it would be feasible, and concretely, I think the simplest way forward to go with that kind of vision is to use the lambda calculus as a semantic base, and then to add extensions. One extension for temporal logic, one extension for the default logic, one extension, and then you will try to reconcile all those logic to get together with some compilation to the same intermediate presentation, for instance. And building bridges between the languages and between the new language that you create and the existing frameworks that has been around that are mainstream is critical, because you don't want your domain-specific language to live itself on an island where it's not connecting to anything else. And building those connections, I think, is paramount, and I've tried to do that in my work.
So Catala could be a part of this?
Yes, I think so.
My second question is, again, about Catala. You use it to I don't know, to represent, to specify, describe the law, and actually is there really something specific to the law, or can it be used for any huge text written in a natural language, such as norms or standards? Here I have a SQL in mind, for instance.
Oh, interesting question. I think if the standard or the text is written in the same way that law is drafted, meaning that you have this base case exception dichotomy, and it's written using articles, and then I think you can try and apply Catala. I'm not sure whether it will work, because it really depends on both what the text is talking about, but also the way the text is structured.
It's really a matter of
Yes.
structure.
Yes.
More questions?
Oh,
Okay.
plenty of them, but I will discuss with Danny
Okay,
later.
as you wish, or we can come back later, as you wish. So thank you, Evelyn. Maybe it's time for the advisors to say a few words. All right.
Yeah, start. Okay.
You're
So, Denis had mostly one question, which is you advocate for a cornucopia of ESLs, with each one serving a specific purpose, because that way you can connect with the domain experts better, and that gives a lot more relevance to the verification work. But there's one thing, and I think it was a question from Bass, where you were saying that in the signal work you had two disconnected DSLs, the ProVerif one and
Yes.
the Lodestar one, and the best you could do was kind of put them side by side and do some sort of visual check that they were matching. And we know the answer to that, right? It's like the new line of work is trying to do everything integrated in one language, but then isn't there some sort of frustrating aspect that you either have to have disconnected results that you check visually, or you have to embrace a single substrate to combine things? Do you see any other way to reconcile the tension between very specific things and the fact that you still want to have one comprehensive theorem rather than piecewise theorems that you just kind of hand wave together into a single comprehensive result?
I can see the tension. I think, and I have felt it during my work. The solution is translation. You want to translate from one DSL to another, and you want to translate programs written in a specific DSL to a general purpose proof assistant where the theorem, this encompassing theorem, can be proven. But then this translation poses the challenge of semantics mismatch. You need to, if you really want to have a foundational approach, you need to embed the semantics of your DSL inside the general purpose proof assistance and certify the computation. So in the end, you have to do everything in the monolithic framework. And indeed, I don't think currently that we have a better way to do things apart if you want to have the foundational everything is proven sound approach to make things in the end in the monolithic framework. But then the question I would ask is, do we need all the time this maximal level of assurance where everything is proven sound inside this foundational proof assistance? I don't have the answer to that. I'll leave that to the appreciation of the jury. But I think in certain areas of where formal methods could be applied, we start from so low that even, I mean, going to the maximum level is, of course, desirable, but reaching some kind of intermediate level will also be like a good outcome for the transfer of technology.
All right, so Danny, I don't really have a strong question here. It's going to be more of a comment that it has been a great pleasure having you be a PhD student. This was an excellent talk, and your thesis was very impressive. I think one of the things that I appreciated most about the work that you presented is that you do kind of try to find this balance between pragmatism and foundations. So you do give semantics to your languages, but at the same time, you're really trying to apply them pragmatically. And you have found your little spot on that continuum. It may not be the spot that many of us would have chosen, but you have chosen one and you're sticking to it. A lot of the jury members have gently tried to suggest to you that in order to give foundations to your framework, you will need that one unified framework after all. And but anyway, you have your position and you're sticking to it, which is great. As far as your PhD years Prosecco have been concerned, we have been very happy to have you in our group. I remember a little about a year and a half, 2 years ago, I was busy doing some boarding proof in F-star. You came into my room and you said, oh, Karthik, I have this little side project on the law I've been working on. And if you don't mind, I'm going to spend the next few weeks working on it. And I was completely distracted. I said, okay. And I went back to my proof. And a couple of years later, I find that this is half your thesis. And you have multiple papers and an entirely new exciting project coming through. So well done. And I'm very proud of you. But at the same time, you're a perfect example of what benign neglect in a PhD advisor can do. So I hope all of us can appreciate it. So, thank you.
Thank you for your comments. They're heartwarming, and yes, foundational is important.
Okay, yeah, I remember this expression, benign neglect. Interesting concept. So thank you, Karthik and Jonathan. Okay, well, I guess it's my turn to ask a few questions and conclude. But, yeah, me too. I was also reminiscing about the first time I heard you talk about this side project of yours. I think it was a seminar, pretty much here, maybe in front of the other screen. And then your talk was already full of very interesting facts and opinions about how the tax law is implemented in the French system, and how, well, they had both a great idea and a terrible idea to use a domain-specific language that was designed specifically for this use, but that nobody else ever used for anything else later. So that's really a fascinating story for language designers or language people like me. Yes, also for software engineering people, and I hope some of them are listening to your experience. So I had a few questions based on well, mostly reading your manuscript. First questions will be about numbers. So in your study of Mlang, well, one of the nice things about Mlang is that you can implement arithmetic in several ways. So you've tried with floating point numbers, with fixed point numbers, with a few things. Maybe you should try decimal fixed point. Base 10 fixed point numbers. It's the latest craze in the fixed point, in the floating point world. Sorry. So there's a whole new IEEE standard about that. Maybe, and they are designed kind of to manipulate some amounts of money. So maybe that would be interesting. But my more general question is, from those experiments of using different styles of numbers, can you conclude that the French fiscal law is robust against arithmetic errors and fluctuations, discontinuities, etc., or is it actually quite fragile?
This is an interesting question. I may not be able to tell you everything about it, but just the fact that the IEEE 7754 standard has been put into place after the Bull company that manufactured the computers that the French tax authority were developed, so that it might be the case that the French tax authority has computers that have floating command encoding that is different from IEEE 744.
Okay.
It might be the case that they were transitioning to normalized systems. It might be the case that this difference of encoding might cause some robustness issues, as you pointed out. Okay. To that, I will respond that the law doesn't specify the encoding of floating point numbers that you have to use in order to compute it. So you're welcome to try compute it using your own floating point encoding and see what results you get, and see whether the courts are pleased or not with your interpretation of the law.
Okay, yeah, I was kind of expecting this answer, but now I have a second question, which is about Catala. So when now in Catala you have an option, you have an opportunity to make things right. And I've noticed you never talk about numbers.
Yes.
In your formalization, you have booleans and functions, and that's the only data types you have. So what is a good number system for the law?
Well, in Catala, in the implementation, I use Z-arith and rational numbers with infinite precision. So that's your
choice. Okay.
Yes, that's my choice, but it needs to be confirmed with the legal interpretation of what it is. And for the money, I use the integer number of cents. So when you divide, you have to round at the nearest cent. And the question whether it is the right behavior that's expected by the law is still a suspense. It seemed like a good behavior to me, but I actually need to check. And I think this is a gray area where the lawyers, they're not aware of the encoding of the numbers, right?
Sure.
So a whole new statutory law or precedent case is waiting to arrive to settle that debate.
Okay. Okay. So you think rational numbers are something that could be sold to legal people? Yeah. Well, they exist since the Greeks.
Yeah.
So
GMP is efficient enough, right? Because
probably that might work. But yeah. Well, there's the story about an American law that was trying to define the number pi, and ended up saying that, well, for all practical purposes, pi could be 3. But well, I don't know if that's an accurate story. Anyway, let's move on to my second question, which is actually something you mentioned on that day in our first talk, and that you mentioned again in conclusions today, which is basically, yeah, if you have a piece of code that is equivalent to the law, or you're pretty sure it is, now you can model check expected properties of the code, and that will model check expected properties of the law. So I think one example you gave was progressivité de l'impôt. I'm not quite sure how you say that in English.
progressivity, tax progressivity,
something like
progressiveness.
That. And that sounded extremely a very exciting prospect. And there's probably others, as Sarah Lowski mentioned. Maybe while the law is drafted, you want to find out loopholes in advance and not wait for the law to come in force. And so basically, there's a whole new area of formal verification that opens. So what are the? But you haven't done it yet. So I guess there are obstacles. So which obstacles do you see? How would you go about that?
Great question. As you said, I haven't had the time to do it yet. I plan to do it in the future years, so we'll see what comes out. I think the biggest obstacles will be, I don't know whether existing off-the-shelf proofers are robust and mature enough to handle the code that comes out of encoding the law. Because if you look at the income tax, it's 100,000 lines of arithmetic. And I think Raphael, who's in the room, tried to just plug that into the MOPSA static analyzer, which is like something, and it just exploded because there's too many conditions, too many variables, too many things, and the context just explodes because you're not supposed to have 40,000 variables inside one function, right? And this is why I presented to you that maybe proof by refinement strategy, where we refine the program and simplify it before sending it to provers, because I think it's going to be one way to bypass that obstacle of the complexity of the code and the fact that it is completely spaghetti code, and that we can't use the traditional method of like chopping up into bits of function with contracts to divide it.
That's true, although, well, fully automatic tools often just expand the functions first. But okay, I understand your point that even for fully automatic tools that are used to big spaghetti code, this is still too big.
Perhaps it will work, and I would be very glad if it worked, but I haven't tried in person.
I don't know. Okay, but that's certainly something to look forward. And maybe, maybe last question. So still about how you use Catala. So you showed relatively small examples where you take one article of one law. Well, it's a big article, a complicated law, but still, and then it turns into half a page of Catala code. And then at some point you also say, but we also need computing expertise to structure the whole code. So how do you structure Catala code? What are the mechanisms you have in the language, and how do you think you're going to use it? Like one article is one function, one law is one module, or something a little more sophisticated than that?
So we currently have one abstraction mechanism in Catala, which is the scope abstraction, which amounts to a function.
Okay.
And then we're planning to have a module system. And then we've encoded the whole computation of family benefits as a motivating case study, and it works. It's around like 1,000 lines of code, so it's medium-sized example, I would say. And we've noticed that at first we really wanted to use many scopes, like one scope per like little computation. But the fact is that you can't do that because everything is interconnected. So we in the end we used like 3 or 4 scopes for the whole computation. And the problem is really that you're trying to put structure into the computation that's defined in the law, but the lawyers they don't need structure. So when they draft the text, they don't think about software engineers trying to put abstractions. So in the end, you're really trying to put some abstraction as much as you can, but even with that like leaky function mechanism that we provide, you can't abstract as much as I wanted, for instance. But you can still do it because you can it's 3 or 4 scopes. It's not one scope, right? So and the module system, it would be, for instance, the computation of how much the SMIC is. It's relatively self-contained, and you can put it in one module. And the design rationale for the module system is that one module is one compilation unit, meaning that the code from one module will not be able to redefine a variable inside another module, and that puts a strict abstraction barrier. Unlike the scopes, where the scopes you can actually modify things, it's a porous abstraction barrier. Hand wave it. So it may be the case that we think that okay, we can put things into 2 different modules, and then there's a horrible article of law that breaks your abstractions, and then you need to fuse the modules together. That I don't have a good answer for. Empirically, most of the production code I've seen is just one big module of spaghetti code and no functions, and everything is variable. So I don't see a rosy future in that regard.
Okay, well, thank you for your answers and for your work. Are there any more questions from the jury? Let's see, nobody is raising their hands.
Nodding.
All right, yeah. Well, we have time to take 1 or 2 questions from the audience, if you want. Okay, well, if not, well, we're going to move to another room for the jury discussions.
There's one question.
Sorry, go ahead.
We talked about tax loopholes. Do you have some kind of
No. But you should ask Sarah Lowski.
Or your accountant.
Yes.
All right, any more questions? All right, well, thank you all.
All right, guys, so we're going to leave the jury. We're going to leave this, and we're going to go to the other room, and we're also going to go to the other Visio.
Yep.
And so
Sorry, Kartik?
Yeah.
Did you send us this link? What was the name of the email in which you sent us this link?
It was a follow-up meeting. It's called GoToMeeting. I'll send you again in a few seconds if you don't find it.
Okay, thanks.
Thank you very much for having come to my defense. For those of you